this video is for Math 112 for section 4.2. This is a continuation of a discussion of the law of sines. So let me write out the law of sines here. Alright, so sine of A over the side A is the same ratio as the sine of angle B over the side B, which should also be the same as the sine of angle C over side C. And again, these can be flipped around. I was using this format in section 4.1 because we were only solving for sides and not for angles. When we're solving for angles, I'll probably use this. And there's no reason you can't use this to solve for the angle, it's just the algebra is a little bit more complicated. Okay, so getting back to why was I always using this in section 4.1 was because we were only looking for sides. So why were we only looking for sides in section 4.1? Why didn't we have any problems where we would be looking for angles? Okay, here's why. So we go back to our diagram about what's positive in which quadrant. Okay. So the sine function has the unique ability to have two different angles have the same sign and also fit into a triangle. Okay? So obviously all of these first quadrant angles between 0 and 90 degrees can fit into a triangle. Okay? None of the angles in the third and fourth quadrant can fit into a triangle because they're all more than 180 degrees, right? Any angle that's down here, right, is going to be more than 180 degrees, and the same thing for the fourth quadrant. So those angles obviously will not appear in a triangle, okay? But a second quadrant angle can appear in a triangle because it's less than 180 degrees. It's going to be an obtuse angle, right? But we can still make a triangle out of it. Okay, so what does this have to do with the law of sines? Well, the issue is, just like we saw in chapter 3 when we were solving trigonometric equations, right? If we say sine of theta is 1/2, then theta is the inverse sine of 1/2, and that's going to be 30 degrees. But right, there's also another angle in the second quadrant with a reference angle of 30, and that is 150 degrees. So we get multiple possibilities when we take the inverse sine here, okay, for what the angle theta could be. It could be 30, it could also be 150. The thing about the sine function is that both of these angles can live in a triangle. So there are some situations where we may not know which one of these we're talking about, okay? All right, so in the textbook in section 4.2, I lay out these three possibilities for solving a triangle using the law of sines. And the three possibilities are one triangle, two triangles, or no triangles. Okay. The textbook lays out sort of the relationship between the values that you're given in the problem and whether you're going to end up with 1, 2, or 0 triangles. It's interesting. I'm glad that I included it, but I'm not sure how helpful it is. Okay, so I think the best way to talk about this and the best way to approach it is just to look at the three examples that I've done in section 4.2. Okay, so I won't talk about beforehand how many triangles we're going to end up with. Let's just look at the problem. All right, so angle A, so this is example 1 from page 142. Angle A is 112 degrees. Side A is 45. Side B is 24. Okay. Well, then we can use the law of sines to find angle B. So, again, I'm going to use this setup now, where I'm going to say sine of 112 over 45 should be equal to the sine of B over 24, and then all I have to do is multiply on both sides by 24. And so, let's see what we get here. Sine of 112 divided by 45 and multiplied by 24. So that says the sine of B is going to be about 0.4945. And again, I'm rounding it off to write it down, but I've got the full thing right here on the calculator. So when I do inverse sine, I'm not going to round it off. I'm just going to do, what is it, second negative sign right here to get that full answer into the inverse sine. And that tells me that B could be 29.6 degrees. Okay? Well, would that fit into a triangle with a 112 degree angle? Yeah, it would. Okay, so that's a possibility. Now remember that in the second quadrant, the sine is also positive, right? So we could have a reference angle over here of 29.6 degrees, and our second quadrant angle in this case then would be, what, 150.4 degrees. Okay. Now, this one we can see makes sense with the problem. Could you fit a 150 degree angle into a triangle that already has 112 degrees angle in it? No. No, you can't. Okay. So, we reject this possibility because we've already got an angle more than 90 degrees in the triangle. These two angles will not fit into the same triangle. Okay, so that's why we reject this answer. Alright, now that we've done that, that says we're only going to get one triangle. Okay, there's angle A, there's angle B. We can subtract from 180 to find angle C. 112, 29.6. 38.4 is what I'm getting for angle C. And then we can use this same ratio to find side C. Okay, so we'll say 45 over the sine of 112 equals side C over the sine of 38.4 degrees. So 45 divided by the sine of 112 multiplied by the sine of 38.4 degrees says that side C should be approximately 30.15. Okay, and let's see, does this work? We got the longest side across from the biggest angle, the shortest side across from the smallest angle. Okay, that's good. Again, if you want to check it again, double check these ratios and make sure that you do get the equality given to us by the law of sines. Okay, so that was the one triangle example. Alright, and we got one triangle because this other possibility wouldn't fit in a triangle with an angle that we already knew we had. Okay, that's example one. Example two. Okay, in example 2, we've got angle A as being 38 degrees. This is on the next page, 143. So, angle A is 38 degrees, side A is 40, side B 52. Okay. Well, let's go ahead and set this up here. We're solving for an angle, so I'll put the sines on the top and the sides on the bottom. Sine B. Okay? So then we're going to do sine of 38 degrees divided by 40 and multiplied by 52. Says that our sine B is going to be about 0.80036. And then we'll do inverse sine of that. And that tells us angle B is approximately 53.2 degrees. Okay? And then also, again, we need to consider the possibility of a second quadrant angle with a reference angle of 53.6 degrees. And that's going to give us 126.4. Okay, so we'll put our 53.2 up here. Okay, so that works. Now, could we have an angle that's 126.4 and an angle that's 38 degrees? Yeah, we can. Okay, so here's one possibility. Here's another possibility. Angle A is 38 degrees. Angle B is 126.4 degrees. And let's see here. What would that make? Angle C, 15.6 degrees. Okay. Up here, 38 and 53.2, that would make angle C just short of a right angle, 88.8 degrees. Because now this adds up to 180. This also adds up to 180. So we don't have a length for side C. Let's see, A is 40, B is 52, and again, we don't have a length for side C yet. We'll find that in 1 minute. Okay, so I've got some diagrams in the textbook here that show how this is happening. This is from page 144. So if we start out, let's see here, with our angle A being 38 degrees, side B is over here being 52. Now side A can happen in two different ways. So one way it can happen is if it comes down like this as 40, and then let's see here, this is B, A, and C. This is the one that makes angle B 126.4 and angle C, this little tiny one, 15.6 degrees. Okay? Now the other thing that you can do starts out the same way, 38 degree angle for A, 52 length for B, and then take that 40, that side of 40, and move it over here. Okay? There's B. There's A, that's 40, that's 52. But in this case, angle B is 53.2 degrees, and angle C is 88.8 degrees. Okay? So that's how we can get two possible triangles from this ambiguous information that we've been given to start out with. Okay? And you can see, in each case, angle C is going to be different, and as a consequence, the length of side C will also be different in these two possibilities. Notice that even though angle B changes between these two possibilities, the length of side B stays the same. Okay? So, not surprisingly, this is called the ambiguous case of the law of sines. And so this is a situation where we get two possible triangles, and we need to set up both of them. Okay, so now that we've got all that taken care of, we need to make two calculations for the length of side C. Let's see here. So in this one, we'll say C over the sine of 88.8 degrees equals 40 over the sine of 38 degrees. And let's see what we get here. 40 divided by the sine of 38 degrees times the sine of 88.8 gives us 64, what are we rounding to on the lengths, 2 decimal places, 64.96 as a length for side C. For this one, let's see, we say C over the sine of 15.6 degrees equals 40 over the sine of 38 degrees. Okay, times the sine of 15.6, and that tells us that C is approximately 17.47. Okay, so there's our 2 possible triangles for this, the ambiguous case of the law of sines. And in reality, we haven't been given enough information to figure out which of those triangles we're supposed to be talking about. Okay, one more example. Example 3. You could probably guess that this is going to be the one where we have 0 triangles. No possible triangles. All right. Example 3 on page 145. We've got angle B at 73 degrees and side B at length of 51. Let's see here. All right. What else? Side A equal to 92. Angle A, we don't know yet. Okay, so if we want to find angle A, we'll say sine of 73 degrees over 51 equals the sine of A over 92. All right, so then we say sine of 73 divided by 51 and then multiplied by 92 says that the sine of A is going to be about 1.725. Well, if you remember, there's no real solution for this. You can't have a real valued angle that has a sine greater than 1. All right? And even if you don't remember, when you try to do the inverse sine, you'll get an error. Okay? So, no real solution. Let's see here. So what does this triangle look like? Let's see here. I think what's happening here is that we've got this 73-degree angle and a side that is 51, right? And then the idea here is that this side is not long enough to complete the triangle. Okay? If you look on page 141, there's 2 of these no triangle situations, and in both cases, the side is just not long enough to complete the triangle. Okay, so those are all the 3 possibilities, and now we've got a bunch of problems on page 147, and we'll just work our way through them. And like I said, some of them there'll be 1 triangle, some of them there'll be 2 triangles, and some will have no triangles. So let's see what we get working our way through here. Okay, problem 2. We've got angle B at 40 degrees, side B is 4, side C is 3, and we need to know what are angle C, angle A, and what's side A. Okay, so let's see here. Let's find angle C first, so we'll say sine B, we know that B is 40 degrees, so sine of 40 degrees over 4 equals the sine of c over 3. So sine 40 divided by 4 times 3 tells us that the sine of c is going to be about 0.4821. And then we'll take the inverse sine of that, and that tells us that c is going to be 28.8 degrees. Or it could be 151.2 degrees. Okay, now let's see. Can this one fit in a triangle with a 40-degree angle? That's the question you need to ask yourself. You're always going to have two possibilities here. The question is, do one or both of these possibilities fit in a triangle with the angle that we already have? We've already got the 40-degree angle. This angle, no problem. 28.8, that fits in a triangle without any problem. This 151 is too big. 151 plus 40 is 190 degrees. That's more than a triangle, a plane triangle on a flat surface can hold. Okay? If you ever take a course in advanced geometry, I never did, but it's pretty interesting stuff because you move beyond what's called plane geometry to consider spherical geometry. Because on a sphere, a triangle can have more than 180 degrees. If you think about it, you know, on a sphere, this is a right angle, this is a right angle, and this is a right angle. That triangle has 270 degrees in it, okay? Spherical geometry is different. And then you get this thing that's called hyperbolic geometry that I'm not even really sure how to draw. This is one way that people draw a hyperbolic geometry, and what happens is that the sides get kind of scrunched in, and you get less than 180 degrees in a triangle because of the way that the figure is distorted. You can see this one is kind of bowed out, so the angles get bigger. This one is kind of scrunched in, the angles get smaller, and that's just different from what we're used to on a flat plane geometry triangle, where the angles are always 180. Okay, a little bit aside there, something I've always found interesting. And the spherical one is very interesting because we live on a sphere. I mean, that's why it's important. Okay? People have theorized that the hyperbolic shape has something to do with the shape of the universe. That's something Einstein was into. I don't know. You know, and it's difficult to talk about the shape of our universe and the nature of time and space. So we'll just kind of leave that off for another time. All right, so we've got two angles. We know we're only going to have one triangle to work with. So we add up the 40 and the 28.8, and that would make angle A 111.2 degrees. And then we'll find side A. So 4 over the sine of 40 equals A over the sine of 111.2. So 4 divided by sine 40, and then we multiply the sine of 111.2, and that says that side A is going to be about 5.80. Okay, so there we go. We've solved the triangle. There's only one triangle. We've got all the angles. We've got all the sides. Okay? Well, let's keep going. Round 4. Angle C, 20 degrees. Side C, length 43. Side A, length 55. We need to find angle A, angle B, and side B. All right. Notice that the length of side A is bigger than the length of side C. That says that angle A should be bigger than this angle C. Let's see. So sine of 20 over 43 equals the sine of A over 55. So sine 20 divided by 43 times 55 says that the sine of A is going to be about 0.4375. And then we'll take the inverse sine there, 25.9 degrees for A. Okay, and then also subtract that from 180. A could also be 154.1 degrees. Okay, let's see, would that fit in a triangle with a 20-degree angle? It would, just barely. This would make 174 degrees. All right, so we're going to need a second triangle over here. 20 degrees for C. A could be 154.1, and that would make B into this little tiny thing. Let's see here. 154.1 plus 20 minus, subtract that from 180. Yeah, that would leave B as being 5.9 degrees. All right, well that still works. The other possibility here is the 25.9 degrees. And that would be, what, 45.9. So that would make this one 134.1 degrees. Okay, so we've got two possibilities for angle B, two possible triangles, and now we just need to find the two possible lengths for side B. All right, so here we're going to have 43 over the sine of 20 equals B over the sine of 134.1. 43 divided by sine 20 times the sine of 134.1 says side B is going to be 90.29. Okay, and then this one down here, 43 over sine 20 equals B over the sine of 5.9. 43 over the sine of 20 times the sine 5.9, 12.92. Okay, and that's the shortest side, that's the smallest angle. Side A is longest here in this triangle. Here in this triangle, side B is the longest one. So we've got two triangles, two possibilities. That's the way it goes. All right, let's look at a few more of these. Problem 6. Okay, angle A is 75 degrees. Side A is a length of 3. We don't know angle B, but side B is 8. And then we don't know side C or angle C. All right, so let's see here. We want to find angle B. So we want to do the sine of 75 over 3 equals sine B over 8. So sine of 75 divided by 3 multiplied by 8 tells us that the sine of B, 2.576. No good. No triangles. Okay? No real solution. There's no real valued angle that has a sine of 2.576. Okay. Well, that's good. So we saw one of each of the possibilities in problems 2, 4, and 6. Okay. So let's take a look through. We'll do another 5 or so problems. We'll see what we come out with on these. Let's see here. Let's look at problem 12. Here, angle C is 27 degrees. Okay. Side C is a length of 37. We don't know angle A, but side A is given to us as 42. And then we're going to look for angle B and side C. Side B as well. Okay. Let's see. So we want to set this up to find angle A. Sine 27 degrees over 37 equals the sine of A over 42. Alright, sine 27 divided by 37 times 42 says the sine of A is going to be about 0.51534. And we'll take the inverse sine. And that says that angle A is going to be about 31.0 degrees. Okay. Subtract that from 180, and we could also have an angle of 148. I guess it's going to round up to 149. 149 degrees. Would that fit in over a triangle with a 27-degree angle? Looks like it would. Okay. Because that would only make 176 degrees. Now, again, that would not leave a whole lot of degrees for angle B, but the size of angle B is not important. The question is it possible? And in this case, it is. So we've got angle C as being 27 degrees, and we could have angle A as being 149 degrees. Okay, so if that's the case, this is going to be 176. That would be 4 degrees for angle B. It's going to have a very short side to go with it. Over here, 27 and 31 makes 58. So that would make this 122, right? 122 plus 58 makes 180. Okay. Excuse me. All right, so what do we need now? Looks like we need to find the length of side B for these two different triangles. Okay. Okay, let's see. Side C is 37, side A is 42. All right, so we'll say 37 over the sine of 27 equals B over the sine of 122. And what do we get here? 37 over sine of 27 degrees times sine of 122, 69.12. Where did I ask for a rounding here? Yeah, side lengths to the nearest hundred. 69.12. And then down here, we'll set up the same thing. 37 over the sine of 27 degrees equals B over the sine of 4 degrees. Times the sine of 4 degrees. 5.69. Okay. So, there we go. That one had two possible triangles. Let's look at problem 14, see what we've got there. All right, 14, angle B, there we go. Angle B is 115 degrees. Side B, 68. Side A is 92. We need to know angle A, angle C, and side C. So, even before we start on this one, there's no way we're going to fit a second quadrant angle in the same triangle as this angle right here. So this problem is either going to be 0 or 1 triangles. We can't have two here. And I'll reiterate that as we work through this. But, So we're going to say sine of 115 degrees over 68 equals the sine of A over 92. Now this angle, notice how this side is even bigger than this side, which says that angle A should be even bigger than angle B. That tells me this is probably a no triangle situation. Let's find out. Sine of 115 divided by 68 times 92. Yeah, sine of A ends up being bigger than 1. 1.226. No real solution. 0 triangles. Okay? You can't have this length being longer than this one if this angle is already more than 90 degrees, you know. Because you can't fit, the other angles in the triangle have to be smaller than 115. That means the sides also have to be less than 68. All right, so that's problem 14. Let's take a look at 16. Okay, problem 16. We've got angle A as being 28 degrees. Side A as being 4.3. Side B is 3.5. And we want to find angle B, angle C, and side C. All right, let's see here. Which one? All right, yeah, so we're going to say sine of 28 degrees over 4.3 equals the sine of B over 3.5. Okay, sine 28 divided by 4.3 multiplied by 3.5 says sine B is going to be about 0.3821. So we take the inverse sine of that, and angle B is going to be about 22.5 degrees. 22.5 degrees. Or, subtract it from 180, it could be 157.5 degrees. Let's see, would that fit into this triangle? No. Too much. 157.5 plus 28 is going to be over 180 degrees. It's going to be 185 degrees or so. Okay, so this one is not possible. All right, so good, that's less work. Angle C should be 129.5 degrees, just by subtracting these two from 180. And then we can say, what, 4.3 over the sine of 28 should be side C over the side of 129.5. Sine of 28, and then multiplied by the sine of 129.5. That says side C is going to be about 7.07. Okay, so that one turned out to be one triangle. All right, so we've seen two of each type of problem. I think I'll do one more example here. I'll just do the last one on the page and see which one it is, see which type of problem it is. Let's see here. Problem 20. Let's see. Angle C, 65 degrees. Side C, 7.1. Side B, 7.6. Angle B, we want to find angle B, angle C, and side C. Okay. So, sine of 65 degrees over 7.1 equals sine B over 7.6. 5 divided by 7.1 times 7.6. So, sine B is going to be about first sign for that. We get angle B. It's going to be about, what are we rounding to? The nearest tenth of a degree. That would make this 76.0 degrees. Okay, subtract that from 180, and that makes 104. Would a 104 degree angle fit in a triangle with a 65 degree angle? Yeah, it would. Okay, so we're going to need two triangles on this one. Sides, angle C is going to be 65. Angle B, the second possibility, could be 104. And what would that leave for angle A? That's 169. That would leave 11 degrees for angle A. Oh, over here, these should be A's. There we go. So in this one, 65 and 76 is going to make 141. And that would leave 39 degrees for angle A. Okay, so we've got all the angles for the two possible triangles. We just need to find the two possibilities for the length of side A. All right, so 7.1 over the sine of 65 equals A over the sine of 39. 7.1 divided by the sine of 65 times the sine of 39. 4.93 for A, and that one. Over here, 7.1 over the sine of 65 is A over the sine of 11 degrees. All right, let's see what we get here. Sine 65 times the sine of 11, 1.49 for the length of A. Okay, and that works. A is the shortest side and the smallest angle in both triangles. All right, so that is and what happens to the law of sines when you don't have enough information. Okay, so let's see here. We've got next week we will look at sections 4.3 and 4.4. Section 4.3 is about the law of cosines, and that's helpful in situations where you can't use the law of sines, because there's two possibilities here where you can't use the law of sines. Okay? We don't have any angles. How can we find out what the angles inside that triangle are? We can't use the law of sines because we don't have any angles to set up in a ratio. Same thing happens if you've got, let's say, this angle is 30 degrees, and this side is 7 and this side is 10. Again, we don't have any pairs. We've got an angle now, but we don't know either of the other two angles, and so we don't have a complete ratio. Notice in all of these problems, I'm starting with a complete ratio where we know both the angle and the side. Okay, and that'll allow us to solve for the unknown piece that we're looking for. Here, we don't have a complete ratio. We would have two missing pieces rather than just one, and so it would be difficult to solve for that. And the law of cosines is really helpful in both of these situations. So that's section 4.3. Section 4.4 is some more application problems using trigonometry, law of sines, and the law of cosines. We can still use right triangle trigonometry sometimes. I think it's a little bit easier, a little bit more straightforward, but it's also less useful. All right. As always, if you have any questions about any of these problems, please let me know. Thanks.